So in the previous video, we introduced this concept of a wave function. A wave function is a hallmark of the quantum mechanical model of the atom. And this wave function deals with the wave-like properties and the particle-like properties of an electron, and it seeks to explain where an electron is most likely be able to be found in an atom. So it's this wave function, specifically the square of the wave function, that relates size, energy, and shape and orientation of this area of space where an electron is. And as I promised you in the previous videos, we're not going to be doing the actual differential equations, the actual calculus to get the solutions to these wave functions. We are going to just talk about the rules for determining the solutions for those wave functions. Those solutions to the wave functions are called quantum numbers. These quantum numbers, they think of them as like the address or the email address for location of an electron in a particular orbital, in a particular region of space. So the quantum numbers that we are going to talk about in this chapter there are 3 of them. We will introduce the 4th. There's a total of 4 quantum numbers. We will talk about 3 of them in this chapter, and these 3 quantum numbers are used to characterize an orbital, a region of space where the electron is. These quantum numbers, they come from solutions to Schrodinger's equation, the math of which we're not going to do, but there are some rules that are associated with quantum numbers that you do need to know. So I really should have a big star on this page. But we will do a practice problem with predicting quantum numbers in the next video. In this video, we're going to introduce these 3 quantum numbers, what they are, what they explain, and what the rules are. The first rule, or the first quantum number, is the principal quantum number. It's given by the variable n. Think about this principal quantum number as synonymous with the energy of an orbit in a Bohr model. Okay? In the quantum mechanical model, the principal quantum number describes the size and energy of the shell of where that region of space it is for an electron. So principal quantum number, designated by an n, allowed values for n, because these values are quantized, they have specific values. Values of n begin with 1 and go up to infinity, depending upon the size of the atom. That's the first principal quantum number. And one other point, principal quantum numbers that are larger have more energy. Specifically, an n value of 3, that shell is going to have more energy than an n value of 2 or 1. So that's the first principal quantum number. Second is something called the angular momentum quantum number, or it has this letter of L for its designation. The angular momentum quantum number indicates the shape of the orbital, or the shape of the region of space. The angular momentum quantum number is going to be related to the letter of the orbital that is assigned. We will talk about letters of orbitals in another video. For right now, you should know the definition of angular quantum number and know that the values that L can have are dictated by the associated value of n. So for any particular value of n, the associated L values start with 1 and go up to a maximum of n minus 1. So for any principal quantum number, you are going to have a range of angular momentum quantum numbers, starting at 0, going up to a maximum of n minus 1. Okay. We'll do an example problem of this in the next video, but you should know that designation and the definition and that rule. The third quantum number is the magnetic quantum number. The magnetic quantum number is related to the orientation that that region of space has. And just like values of L were dictated by values of N, the magnetic quantum number values are dictated by values of L, or they are dependent upon values of L. So given a particular L value, the M of L, the magnetic quantum number, has a range of values from negative L to plus L. So those are the rules for determining those three quantum numbers and what they relate to. In the next video, we're going to talk about how to use those rules to determine specific values of those quantum numbers for particular atoms.